All right. All right. Hey, Deepak. Hey, Ranbir. Hi,
Hey
Ruth.
Sandeep, very good
Hi.
evening.
How are you doing, guys?
Doing good, thanks. Just got up.
You just got up?
Yeah,
Okay. Okay.
yeah.
Perfect. 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 Okay. My question to all of you is that uh, do you think you have become better because of these classes?
So I can,
Yes.
yeah. So uh, honestly, Sandeep, yeah, obviously I've become better and I've gained new knowledge about the subject. But unfortunately, I haven't been able to give that much time as I'm supposed to. So, like for example, I think the first 2, 3 months we covered the Python programming, right, language. I haven't actually uh, even tried anything on most of the assignment. I mean, obviously, I know I will pick up Python with my programming and the software development background, but a lot of things I've learned a lot, that is for sure. But I definitely need to give more time to this.
Okay.
But yeah,
Okay. Okay. Okay.
so to answer your question, yes, I've become better, but yeah, I think I haven't been able to do justice.
Okay. Okay. All right. All right. And yeah. So my request to everyone would be that whatever happened, happened. You did not have time. We all have, right? I mean, doing uh, such kind of intensive course along with your job, along with the family, along with hundreds of kinds of, you know, things that we have is really hard. And I can tell you, based on my observation in here, when I see the companies which are French or European, okay, I can tell you that, and the Indian companies or the engineers in India work like 4 times than any of the European companies. Okay. So we don't have much time. Yeah, that's what I see. We don't get much time for anything else. So I think, uh, given the fact that most of you are doing job, it's actually commendable that you're able to dedicate your time to the class. Okay. Because I know for sure, like when I was with Amazon, I used to go early at 6 o'clock, 6:30, and I used to come back by 6:30 or 7, or maybe sometimes 7:30 because of the traffic. Okay. So it just took away all my time. I had no life. You know, when I go to office, my kid used to be sleeping, and when I come back, my kid was sleeping. And 1.5 years, and I was sick of the job. Okay. I said, this much money I can just make out of sitting at home. Okay. And I started just teaching people, even my boss from Amazon actually attended my classes, and a lot of people actually, and it just worked out. Used to call this thing as no big data, KNOW, big data. That was my the online courses, and I started with MongoDB, Hadoop, Spark, and everything. It turned out pretty well. So all I can say is that that job at Amazon was probably much more draining, right? I mean, I couldn't. I used to wait for the weekend to come so that I can spend some time with my kid. And like whole week, I would see him just sleeping. Okay, it used to be very frustrating. So yeah, I think given the fact that most of the companies are this kind of time consuming, you guys attending this class is extremely I mean, it's a big, big thing for me. It's a big thing. I consider it as a testimony that all of you are coming, to the classes, and that's why I want to make sure that I do justice to these classes. It's not only the money, okay? It's more about, all of you spending your valuable hours, valuable time, yeah, into learning something. That's why I want to keep things that at the bottom. Keep going, keep going, keep going, keep going. Okay. Now, if you notice here, line number 98, 99, right?
Yes, sir.
97, 98, 99. You see, the loss is still dropping, correct? That
Yes,
means you need to increase your epochs. Got it? You
yes, sir.
need to increase your epochs. All right. So that's all. All right. So that essentially is, the crux of it. And essentially, yeah, essentially, this is a very, very important thing. Okay. So when instead of like tomorrow, if somebody says, how much should be the eta, right, in an interview, like the interview questions would look like this. Okay. That what would you do if your loss function is still decreasing? How many loops would you run for how many iterations will you train your model? That's the question. So what will be your answer to that? For how many loops, like how many epochs should you train your model? Go ahead.
Yes, sir. So in this case, the range which I kept was from 0 to 1,000. So to ensure that we are reaching up to the error point in the smallest way and to get the most approximate value out there.
No, epochs, how many epochs? 1,000 epochs.
Yes, sir.
No, the interview question is that how many epochs what is epoch? Epoch is nothing but one training loop, correct?
Yes, sir.
Eh, Basically, you're tweaking the weights once. Tweaking weights once is called one epoch. For how many times should you tweak the weights? That is the question. Should it be 10? Should it be 20? Should it be 100? Should it be 1,000? Should it be 5,000? How many times?
And the error
Um,
rate is very small, very, very, very small.
When you should keep running the loop as long as the error is dropping. Okay? As long as the error is dropping, you should keep running the loop. And the moment error stops dropping, or the error on the test data, unseen data, when it starts increasing, you should just stop it there. Okay, because that's too much of memorization. Okay. All right. Yes. Now, other question. Usually, in interview, people would ask that the how much is the eta? Everybody knows the answer now. How much should be the eta?
So
Point
'Cause
0.002,
very, yeah, no,
very
or
low. We
even
should.
yeah, even less than that, right?
Yeah. It is up to, if your loss is exploding, if your loss is increasing, keep decreasing your eta. Okay. And that. And we will learn about in the course, we will learn about learning rate scheduling. Learning rate scheduling is like this. Initially, keep the eta to be very small. Sorry, keep the eta to be big and then keep it decreasing. Keep decreasing the eta every 1,000 epochs. Or every 10 epochs, keep decreasing the eta. Initially,
So,
keep the eta
so
high.
in the same program, you are saying we should decrease it after certain number of epochs.
Yeah. We call that a strategy as learning rate scheduling. So what people do is they keep on decreasing the eta. Every 10 epochs, they divide the eta by 10. Or basically they make it like every 100 epochs, divide the eta by 10. Okay, because when you're about to reach the loss function, you'll kind of become, if the eta is very big, you'll keep on jumping back and forth. Okay, and that's why you have to slow down there when you are reached the loss function. Otherwise, you'll keep on jumping back and forth. Okay, so that is called learning rate scheduling. So that's an advanced answer. That usually you should keep an eta such that my loss function should not increase and it should not bounce away. And but further, if based on the problem, if it seems that we need to use the learning rate scheduling, we can use the learning rate scheduling. Okay, good. Everybody's okay. All right, so that's it. That's it. You've all learned machine learning. Okay, that's about it. Okay, all right. Now, in some cases, right, when the data is given to you, you don't know whether a line will fit into it, a circle will fit into it, cube will fit into it. You don't know what will fit into that data, right? That's why you come up with all kinds of mathematical formulas. Okay, and essentially, one of the assumptions was that we can have, right, lots of more weights and parameters of n degree polynomial, and people have been doing all of that. Okay, now let me go back to where I was. Okay, perfect. Now everybody is comfortable with, all right. Oh, I have closed that one, but never mind. I will create a new tab. This is all done. All right, perfect. So, okay, this is my today's notebook. I'll create a today's notebook, August 17. All right. Do you guys have any doubts about gradient descent? I want to move on to the second algorithm called normal equation. Okay. I want to go through that one, even though that one is not very important. Okay. But I want to give you a bit of more understanding about it, right? What is the other algorithm that is used in linear regression? Okay. There is a
So,
learning.
yeah, if there are, so in real world data set, if I download any real world data set and if I run the gradient descent, will it work for those as well? Or how
Yes.
can I do it?
Yes. Let's just see. Okay. All right. You can actually just do this. Okay. Let's extend this, not this one. Yesterday's algorithm, shall we take it out? What was the one that we did yesterday? This one, correct? Okay. All right. Let's I think your question is very, very valid. And instead of jumping into the normal equation right now, we will take this and make just one step complex. Okay? Everybody okay with this? All right. So right now, what we did was we did this. Okay? I'm sorry, I need to connect the Zoom meeting to my iPad. Okay. All right. If you guys have any questions on yesterday's thing, please ask right now. We're going to make it a little more complex. Okay? Little more complex.
Mm-hmm.
All right, perfect. Okay. So yesterday, what we did was we had like, if you think of this, okay. Okay. If you think about it, okay. Yeah, what we did yesterday was this, right? And what does it mean? It means that this equation or this system, let's call it a sum function, is taking one variable x and giving one variable y. Okay. Your question would be that what if we had two variables, x1 and x2? Okay. There is a function which is taking two variables and giving one output. How would we construct our model around it? Okay. Like if you take the data, stocks data, it has multiple columns, right? It has first column being yesterday's high value, yesterday's this low value, and then you're predicting tomorrow's high value, correct? How would you deal with multiple variables in the input? So what we'll do is we'll take this, increase one more variable. Instead of only x1, we'll make it x1 and x2, okay? And then generate the data, and then write the gradient descent for that, and then do that. Everybody okay with that?
Yes.
Yes.
Okay. And you'll be amazed that just using that, right? You can actually just use your own algorithm to solve most of the problem. Okay, most of the regression problems. Okay. Including stock price prediction. All right, let's move on. Yeah, this thing is working. My pencil. Good, good. I think we are taking it one more step ahead. Okay, so, all right. Import random, import plotting library, and this time we are generating two things, okay? For, let's say, for x in range 1 to 10, okay? We are also let's say we are generating, okay? All right. Let's just say that, okay? We are saying x1 is random.random. And let's say this is between 0 and 1000. And x2 is random.random. And this one is -100 to 200. Okay. And our output is between, let's say, this and 30 times x2 plus, let's say, 67, and that's it. Okay. So we are saying that we have a secret equation that we know just for generating data, which takes x1, x2, and gives out y. Okay. And this time, instead of appending only x, we are appending a tuple containing x1, x2. Okay. It says that random does not take multiple argument. Okay. So what we can do, okay, we can just let it be like this, okay? Just like this. Okay. So we generated X and we generated, you see the X0, single data point has X1 and X2, right? And Y0 is, capital Y0 is this value. Okay. So I just generated my data. Are you guys okay?
And the value y which you given 100 multiply x1. So this is your hypothetical number. We can take any number, right? The way we want to generate.
This is just for generating data.
Yeah.
Okay. In real sense, instead of generating data, you will take this data from the observations that you have done the observation. That when we fed x1 this much to machine, x2 this much to machine, y1 came. Okay. So essentially, here, okay, here, this is how you should think of this. Okay, this is your machinery. Your machinery is taking two variables, x1 and x2. You don't know what's inside the machine. It is generating y. Okay, so that's how you should think of it. All right, let me see if I can. Okay, will I be able to put it into this notebook? Okay, I'll change it to Markdown. Oh, it did not copy it. Okay, I'll go to recent. Where is screenshot? Where does it keep the screenshots? Is it in desktop? Yeah, here. Okay. Okay, this is how you can think of this. Okay, so this is how this is the data that we have generated. So we are essentially kind of cheating. We are basically generating data for our convenience. In real life, you will basically just get the data from your source, and then you will use that data to do the rest. Okay. For now, for convenience, we are doing that. Okay, just for this class is convenient, but we will show you at the end that we can actually just take the data from anywhere and build the model using that. Okay, now the other important part is that I want to take a data which has some sort of linear relationship. It's not too complex. Okay, and I'll explain to you why later. Now, okay, so this is the data we have generated. Now let's go ahead and write the loss function for it. Okay. Okay. And will it work? Will it be able to plot X and Y? Let's see. Where is plot X and Y? It says you cannot plot X and Y like this. So I will try to generate map X and lambda. I'll just pick up only the first value from each of the tuple, and we have to change the order. Okay, I'll just change the order like this. That's it. It did not work. Why? Matplotlib does not support generators, so we'll just have to convert to list. Okay. Okay, we'll just call it x1 equal to, we separated the x1 to this, x2 to this. Okay, just to plot it. Just to plot it. Okay, so x1 looks like this. Wow, how come? It should be something, linear. Yeah, like this. So x2 and y, how come? X2 is okay, but oh, probably the impact of x2 on y is not significant. Okay. Okay, let it be. Okay, let it be. Now, that's our, the thing. Now let's write wait. Okay, so now the equation for this is going to be, how will it look like? We have x1 and x2, two columns in the input. We don't know what is going to be our weight. So we are assuming here y is equal to w0, w1 x1 plus w2 x2. So we are given x1, x2, and y. We have to figure out w1, w2, w3, right? Correct? We don't know how much are these weights. We know that we are given y and we are given x1 and x2, correct? So what we'll do is we'll just assume. So we are given the data, we have to figure out a relationship. So what we are doing is here, okay? So we are saying take the weights, we'll get an array, w1, w2, w3, like that. And then what we'll do, we will say that these weights we are going to multiply with x1, x2, x3. Okay, so we will be given capital X. We are having this x here, and here is our weights. Okay, now what we have to do, we have to go through all of the x variables and all of the, so for each of the x1, x2 value, okay, and for each of the columns, this is rows, okay, rows. And now we have to go through the columns, okay. All right, I would, instead of saying this, okay, I comma row. Okay, so we are right, we are saying, and we are saying column value equal to how much, equal to how much. We're going to say right, we are saying here for j in enumerate the row. Okay, for the whole row, what is a row for us? x1 comma x2, right? And we are going through x1, x2, and then we'll
I'm sorry, what is this capital X, Sandeep, in enumerate capital? I didn't get that.
yeah, capital X is, if you go up, capital X is a list of tuples. Okay, each record looks like this.
Oh, so that's the data that we have generated.
This is the data that we've generated. X is an array, capital X is an array of tuples. X1, X2. Okay?
Okay, got it. Okay. And when we say enumerate, then it will be for every element in that array.
Yes. Okay. Every tuple. Okay? Okay. So for every tuple, we are converting each of the tuple into this. Okay? And then what we are doing is, this is our predicted y. Actual y is yi. Predicted, actual minus predicted, and this is our total error. Okay?
So, Sandeep, what is the significance of W0, WO, whatever we want to be read? W1 X1, this is a mathematical equation to calculate that? When we have a two variable in the function?
Yeah. We are saying this, okay. It's a very important question. What's the significance of W0? Okay. We are saying that in this is our machinery. We are feeding X1 and this is our output. Okay. We are saying that output is a function of input times some number. If you multiply the input by some number and add something to it, we will get Y. Okay? Like, right? Like in an organization, my outcome is a function of how many hours we have put in times some number plus some value. Correct? And that's a normal phenomena. You must have remembered that, somebody told me, how to calculate your expected salary. If you just do your 10 times if you subtract your age by this and multiply by this, you'll get the expected salary, right? So most of the phenomena in the world are linear regression. Okay, there's a linear relationship between input and output. Okay, like for example, how much pressure should you put on a wall, such that, or let's say, like moving the mouse cursor, right? How much mouse should you move such that the pointer moves by 1 centimeter? So most of these relationships of input and output have kind of linear relationship, that if you multiply the input by some value and add something to it, you should get some outcome. And that's what we are saying here, that I'm assuming that since there are two inputs, X1 and X2, if I multiply X1 with something and X2 with something and then add something to it, I should get an outcome. I just have to figure out what is those somethings. What are those values of multipliers and this thing? Okay, if we did not have this one, right, we could not come up with a good relationship, because right, for example, y equal to mx plus c, the way we drew the line, right? If there was no c, we will be drawing the line from the center all the time. Okay, so we could never reach to a better solution. Got it? No?
But it's not a mathematical formula, right? It's just to bring a linear relation, be just adding and multiplying, right? Those two numbers.
It's a mathematical formula to express that.
Okay.
Express this understanding that if you have a machinery and the output it gives is something multiplied with input plus something extra, that's the outcome. Okay. So essentially, mathematically, this is the equation of a plane. Okay. This is the equation of a plane. Like the way y equal to mx plus c, right? You remember y equal to mx plus c? It's similar to that, and it's an equation of plane. But in practical sense, in a commonsensical sense, what is doing? It's saying that multiply something with input, some constant with input, and add something to it, you should get an output. You just have to figure out those two numbers. Got it?
So we're going to try to find out weight, right? Or we're going to assign some value by default to weight, and then we can get x1 and x2. You're going to get the input, right, as you pointed out, and then we can get the value of y. Y is equal to this.
Yes.
Right.
Okay.
And Sandeep, you are also using lambda. If you go up, what is a function of lambda?
Okay. Lambda is like a quick way of defining a function.
Yeah, here map lambda.
Yeah. This lambda is doing nothing but We are just picking the 0th value from it. And using this map, okay? So see, I could do this this way, okay? I could say my x1, right? I could say for x1 comma x2 in x, okay? x1 comma x2 in x. I could just do this. I could define. Actually, this would have been easier. Okay. This. Okay. And I'm going to say x1 dot append x1, x2 dot append x2. That's all. Okay. Basically, this I wanted to plot x1 versus y and x2 versus y just to see the outcome. That's all I wanted to do. Okay.
Yeah. So either we use a lambda or we use what you mentioned above, right? But both of them are doing the same function, right?
Same.
Because
yeah. Here you see map function. What map does is it takes this function. This is the function. It takes this, run this on each element. I think this is a good point that you have raised. I think I'll just explain to you. Let's say you have 1, 2, 3, 4. Okay. Or let me just take the current example. Okay. Let's say you have an array of 1, 2, 3, 4, and 8, 9, like that, right? And what we want to do is we want to convert this into 1, 3, 8, and 2, 4, 9. We want to separate x2 and x1 like this. Okay?
Okay.
So now this one, okay, this one, what it does, we went through each element. This is our capital X, this is our x1, this is our x2, correct? So what we did here, we went through this list for x1, x2 in x. So x1, x2, x1, x2, x1, x2. And then in x1, we appended x1, 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 in capital X1. In capital X2, we appended x1, x1, here x2, x2. Got it? Sorry, this is wrong. This is capital X2, this is capital X1. Got it? So that's what we did. Here, what we did was problem we solved the same, just that what map does is map takes a function from you, okay, and applies that function on every element. So this function was applied onto this tuple, this tuple, this tuple. So the difference is, in the first approach, we are bringing the data to the for loop. Okay. In the second approach, we are taking the for loop, or we're taking the function to each of the data. So we are passing the function as argument to map. Okay. And what map does underneath? It runs this function against each element, and whatever is the output of the function, it puts it into another array. That's all. So here we pass this lambda function as argument. And what does this lambda function do? It takes a tuple and returns the first value. What does this lambda function do? It takes the tuple, returns the second value of it. That's all. Are you clear with this?
Yeah.
Okay. These two approaches are interesting. Okay. This one is a for loop. Okay. Here you are iterating. Here the iterations, iterating over the data's job is of map. You are only responsible to give a function definition. Okay. Now, why is map very useful? You can give this function to the map. A map might run this function using multiple computers, using multiple cores, multiple threads. It is the duty of the map to do it. Okay. So usually when it comes to big data, you usually just define your mapper functions and you let the system do the iteration for you. All right.
Got it. Thanks, Sandeep.
Okay, perfect. Perfect. Very good questions. And moving on. So now I hope everybody's clear about it.
Yes.
Okay.
So
So
far
if
we are just calculating the mean square loss, right? For every
Mhm.
like using the weights that we will start with,
Yes.
right?
Whatever weight we provide to this loss function, it will go over the whole list, try to predict the value of y and compare it with actual y, and then gives you the total error.
Right. Got it.
Okay. Now, if we had 3 variables in input, how would it look? Who will help me? How would this function change if we had x3 also? Let's say we had one more thing called x3. How will the function look like? Can somebody tell me quickly?
Yes, so it will be W3 into X3 that we have
W3.
to add. And over in the weights, we have to add W3 variable in the
We'll have
second line.
add W3. Okay, I think we'll just put W0 in the beginning. Should we do that? W0 in the beginning?
Yeah.
Yeah, that makes it look nicer. Okay.
And then in the data set, we have to make the changes, right?
It doesn't matter. Yeah.
No, not over here. I'm saying in that X1 and X2, we need X3 as well, right? The append
Yeah. No, that we are assuming that the data set
that is
contains
available.
X3.
Oh, okay.
We are
Got it.
assuming the data set contains X3. Okay.
Okay.
Now, rather than keep on doing this, if there are more values like X1, X2, X3, X4, X5, like 100 columns are there in the data, you have to write and type everything, correct? So your data might have 2 columns, your data might have 100 columns. So you want to make your code such that it can work for all kinds of variables, right? Everybody okay with that?
Yes.
All right. So let's try to generalize it. Okay. Let's try to generalize it. All right. So these are my weights. Okay. So we don't have to do anything right now. Let's write it in a like more general way. We call it, this one is a 2 variable one, this is a 3 variable one, and this is a general one. Everybody on the same page so far, everyone? We are writing a function that tells us how much error is there between actual and the predicted based on these weights. Okay, we are writing a function that computes the error between predicted and actual. Okay, so this is our hypothesis. The weights are our hypothesis. We are saying that this is what I think the weights could be, the W1, W2, W3, and SQL loss tells us that how wrong are these, or how far away are they from the actual. Okay, by converting that into a single number called the total squared loss, right? So let's make a general one where you could have data that have 100 column or 1,000 columns. Okay, so how do you do that? We go over all the rows first. We enumerate over the rows. Okay, let's say this is our row. Okay, this is our row. And then we go over the column. We'll say, okay, we'll go over the columns. All right, we'll say J, comma, column, in, enumerate, row. Okay, and then instead of doing this, we will say predicted y is equals to W0. Okay, W0 means weights of 0. Okay, and then we will add to the predicted y, we'll say predicted y plus equals, okay, predicted y is how much? Okay, add to x1 and W1. Okay, so what we are going to do, we're going to say X1, Xj, or you can say row of J. Okay, or we can actually say small x. Okay, small x. And from this, small x is nothing but the whole row. We are picking the jth column. And from the weights, we are picking the j plus 1, right? J plus 1. Good. And that's it.
Something why +1?
Because the zeroth value is our this. So x1 is basically x0, right? So the equation will look like this, right? The equation actually is like this. Right? If you think about it, this. Okay, let me just put it in comments. So we are saying W0 plus, this is not x1. This is x1 is what? X0, right? The 0th value of row. And this is 1. And this is 2. Make sense?
Yeah. And Sandeep, can we do like when we designing like X1 into W1? Can we only write X1 W1 without mentioning the asterisk sign? Whether do you
Where
work that way? Like
no, in Python we can't say like this, right? X is 1 and W is 2. We can't say XW, correct? XW is a different variable, so you'll have to write like this. Got it?
Yeah.
So like that's the reason. Okay. Perfect. Everybody okay? All right. So this is like W0
Yep.
and X0, W0, sorry, W1, X1, W2, and X2, W3. Okay. Everybody okay so far?
Yep.
Sandeep, maybe you might have covered earlier, but I was asking how we in the real data decide weights, or in the real data, let's say 10 columns are there. So which
Yeah.
column will be decided as weight?
No, we are not deciding on that. We are just choosing weights randomly. Okay. We are going to choose weights randomly, and this function will give us the error. And then we will keep on tweaking each of these weights until our error is going to be minimum. Okay. So x0, x1 is our actual data. And W1, W2, W3, W0, this is our hypothesis. We just chose them randomly. We're going to choose them randomly, and then we will start trying to do guesswork until our error is minimum. Got it?
So by minimizing the error, we are deciding the weights.
Yes.
Okay.
We are figuring out those values of weights for which the error is minimum. Okay?
Yep.
Perfect. So we are given x1, x2, x3, the tabular data. Okay. It has columns. Okay. So the way usually we represent our data is like this. Okay. It's in the table format. Okay. This is x1, x2, x3, and this is y. One example, another example. So the rows are called experience, instances, examples. Okay, the rows are called examples, instances, experience. Okay, and the column are called features. Okay, and this y is our target, or we also call it label. Okay, so we are given the data set that let's say we are given 100 rows. 100 rows. 100 rows are our experience. And we are given 3 columns. Each experience has got this much features. And we are supposed to predict the label Y. Okay? If we are given an image, for example, and you have to predict whether this image is a male or a female. So the column is 0 or 1, Y, okay, 0, 1, and so on. And the row is an image. And what we do is we take an image, try to convert it into X1, X2, X3, X4. Okay. So in case of an audio clip, what we do, let's say we have to predict whether this audio contains a rabbit sound, or a peacock sound, or let's say it's a sound of a human. Okay, so in that case, the sound of a peacock, a rabbit, or human, that will be denoted by 0, 1, 2, and that will be our target. And each row is going to be an audio file. And what will be X1, X2? X1, X2 will be our intensity of sound every millisecond. Every frame is when the sound is coming to your ear, how much pressure it's making on your ear. And those are, can you guess how many numbers are those? For 1 second of data, you have close to, I think, 20,000 numbers or more than that. Okay.
Wow.
Okay, so you'll have 20,000 columns for 1 second of audio clip. Okay, and this is a very important part. We'll come back to that. So what we are doing right now is we are generalizing our strategy that we did for one variable for any number of variable, so that we can use the same model, same strategy for solving all kinds of problems. Okay, are you lost, everyone? No.
Makes sense.
And Sandeep, it doesn't make any impact whether number of row and column is equal or different, right? Whatever it is there, it will calculate, right? Might
Good.
be in data, or yeah, right, in a matrix, sometime row will be more, column will be more or less or whatever. So how it will work?
Very, very important question. Okay, let me ask you this. Okay, somebody gives you a table of X and Y. X1, Y. There's only one column, right? Only one variable, right?
Mhm.
How many minimum rows of data do you need? If you are having Y equal to mx1 plus C, how many minimum number of rows you need? Can you tell me? To solve this equation, you need to find M and C. Okay, how many values of okay, let's say you're given 1 and 3, so we can fit in like 3 equals
Two
to
equations, right? Two equations, so two set of values.
M plus C. Okay, if we get one more equation, okay, there will write 4 equal to x1 plus C, sorry, M, 3M plus C, 3M plus C. Okay, so from these two equations, we can solve the value of M and C, right? So minimum number of equation you need, minimum number of equation is, right? If you have one variable, one column in the features, you need at least two equations. Are you agreeing with this? So if you have F number of columns, you need F plus 1 rows. Minimum. That's minimum. Okay. The more the number of rows, the better it is. Okay. So usually a very important thing what happens is, let's say you are given a data and you have just too many columns and too less rows. Then your life becomes troublesome. So what do? you kind of try to plot the relationship between y1, y and x1, y and x2, y and x3, like that you try to plot and see which one looks more random. We just drop those columns. So we minimize the number of features so that our requirement of number of rows becomes better. I mean, lesser. Okay. So as an important part to understand.
Sorry, what features rows we will draw?
We will try to plot and see, is there a relationship between y and x1, y and x2? Like here, what I did
Okay.
earlier, like the way I did here, there doesn't seem to be a relationship between x and y here. So it's better to just drop it.
Okay. But then that will be all kind of manual means work means
No,
it's
I mean, there are
all your own
algorithms.
discretion or
No, there are algorithms to do that. We call that strategy. We call that a strategy dimensionality reduction. Okay, we reduce the dimensions. Okay, so what we do is we basically just try to drop those values which are not relevant to us, or come up with a better combination that is more relevant. Okay, like for example, if you catch a criminal, right, and you want to store his some evidence that this guy, right, we want to store that his photo, right? So and we have a limited storage, right? So somebody will say, why don't you take all possible photos from all possible angles? Okay, we can take the photos of all possible angles, right, from the head, from the toe, from the back, from everywhere and every angle, just so that we don't miss out anything. The other thing could be we'll just figure out which one is the most important photo, which covers all the features. We just keep those, so we don't have too many of columns. So coming back to the point is that we kind of try to compress the features. We kind of keep the features minimum so that we can draw better draw better results. So we use the algorithm. If our columns are too many, rows are too less, we reduce the dimensions, we drop those columns which are not relevant, we keep only important columns, and then and there are algorithms for those. You will study in the chapter called unsupervised learning. The algorithms such as PCA you'll study in order to understand the dimensionality reduction. Okay. All right. Now, coming back to a very important point. If features are higher, okay, it's a bad news for you. Okay. If rows are higher, it's a good news. Okay. More feature means you need more data. More rows, that means your results will be more accurate. Okay. So I hope you got the picture. So if you have more number of columns, you'll have to apply more and more. You need to gather more data in order to get better modeling. Okay. If you have too few data records, it's going to be painful. Okay. And I hope everybody got the picture. Very, very important questions. Thank you for those questions. Yeah. All right. So we generalized our loss. Everybody okay with this?
In this strategy, do we try to experiment with every combination of W and X, X1, X2? How do we reduce that number of combinations?
No, we are basically just keeping, we are not, no, I'm not getting the question.
For example, we have to vary W, right? So we have some value for W, let's say W0, and then apply it to X1. Then
Yes.
that value increment could have been applied to the X2 also, but we chose to apply it to X1.
Oh,
So
you are saying that, okay, you are saying that, let's say here y is equal to x0 plus w1 x1 plus w2 x2, right? Are you
Right.
saying that instead of this, what if we had x0 plus w1 x1 plus w2 x2 plus w1 x2 plus w2 x2?
No, what I'm saying is that we can have W in the second row, we can have W2 x1 and W1 x2.
No, but why?
So, for example, let's say we start varying these values, right? Weights are random that we decided.
So see, in our data, there is nothing related. This is our data. Y, x1, x2. This is our data. This is my data. Okay. We are saying that y is a resultant of something multiplied with x1, something multiplied with x2, and a constant. Okay. That's what we are saying. And that's common. So those weights are common for all the rows. Same weight is again multiplied here, here, and then added. So weights are constant across all the rows. Got it?
So we are saying we are applying the same weight to all the values like x0, x1 and all.
Yes, yes, yes.
Then when we have this W1, W2, W3, what does it mean?
For each column. Got it?
No. Sorry. So what I'm saying is that if
let's take this
W1,
example. Let's take this example. Okay. So we are saying our error in row 1 is how much? 1 multiplied by W1 plus 2 multiplied by W2 plus W0. Okay. Minus 3. Okay. That's my error in row number 1. Error in row number 2 is how much? 4 multiplied by W1 plus 5 multiplied with W2, okay, plus W0 minus how much? 6. Okay. Error in third row is how much? Error in third row, 8.
so W1 and W2, these are different values, right?
W1 and W2 are, no, this and this are same value.
Then why are we saying W1, W2? We can simply say W, right?
No, W1 and W2 are different. W1 is not equal to W2. W2 is not, may not be equal to W0. They are 3 separate values. So we are trying to figure out those three values, W2, W1, and W0, such that this data fits a straight line, a plane, such that this 8 times W2 plus W0 minus 10. So our total error is E1 square, E2 square plus E3 square. And this is E. Okay. So what you are seeing here, that we are going to take assumption for W2 in one assumption. Okay. Let's say we define W1 equals to, let's say 1, W2 equals to 2, W3 equals to 0. Let's say that's our assumption. We'll take this assumption, compute error in first row, second row, third row for the same with these 3 values, and then we will square all of them and sum it, and that will be our error.
So in the next iteration, we are going to change W1 to what? The next value also. So what I mean is, are we planning? Are we doing all the combinations in here? For example, let's say W1, W2, W3. We assumed we say we'll apply W1 to X1, W2 to X2.
Yes.
But we could have applied, let's say, W3 to X1 and W1 to X3, right? So how do we decide? Are we going to try all these combinations?
Basically, we are doing that, but we are doing it a little bit more sensibly. One way could have been that we try all possible values of W1, W2. We try, let's say, minus 1 billion till plus 1 billion. We try all values for W1, we try all values for W2, and we try all values for W3. How many total values will be there? If we are trying 10 to the power 9 values for each of them, how many permutations will we get?
Yeah, we'll get a lot. That's
We
what my
will
question
get
is, that
10 to the power
yes,
27 permutations.
right.
Okay. So what we are going to do is cleverly observe that should we increase W1 or W2 such that our error, based on whether our error is going up or down. Okay. We could actually do all permutations of W1, W2, right? We could simply say here that, okay, let's say generate, let's say for 1 comma, generate for W1 in range minus 100 to 100, okay, print W1, okay, and then we do the same thing for W2, okay. Is this right? Am I
Yeah,
in the
exactly. That's what my question was.
yeah?
That how do we decide to reduce this
We could
combination?
basically just do this, okay? Right, print here compute loss for W1, W2, W3. Okay, so okay, so like this, right? So you can see minus 100. So you can see all permutations are going to be there. Okay, and how many total permutations will be there? Can somebody guess? 200 this, 200 this, 200 this. Total will be?
200 raised to 3.
Yes, 200 raised to power 3. Okay, you can just do the counts. Okay, but it'll just go bonkers. Okay, I'm just going to comment it out. Okay, all right, still going on. Okay, let's see if it runs. 200 to the power 3 is how much? 8 into 10 to the
8
power
crore, 8 CR. No,
80 lakhs,
80 lakhs.
right? All right, so this goes crazy and I'll have to interrupt kernel. Okay, so yeah, so one way could have been that we brute force our way. We try all possible values of W1, W2, W3. That will become massive. Therefore, we'll go little greedy, a little bit more strategic. We'll tweak the value of W1 slightly, observe the error, then if because of increasing error is going down, keep increasing, otherwise decrease it. Okay, so we'll do a little bit more greedy way of doing it. Okay, all right.
Sandeep, this is still the gradient descent thing, right? With
Which
multiple
one?
weights. This what we are seeing
Which
now, or
one?
this is no, not this one. This whole
Yeah, this
this
is still gradient descent.
still great, because you in the beginning of the class you said you are going to switch to something else.
Yeah,
Normal
I
something.
decided I decided not to do that.
Okay.
Okay, we are going to still go with gradient descent. Just make the problem more general.
General. Okay.
Yesterday we talked about one column in input. Now we are talking any number of columns. Here we talked about 2 columns. Here we talked about 3 columns. Here we are saying any number of columns.
Any
Okay,
number of features basically.
any number of features.
Okay.
Okay,
Thanks.
perfect. All right, I'm doing it for the first time and I'm not done this live in the class. I'm doing it for the first time. So, but and trust me, you the way we are doing is that the answer, the solution that we came up yesterday is a proof that our approach was right. Correct? Just because we were able to, you can see that we were able to bring down the loss and we were able to come up with the solution, right? Okay, that shows that our strategy was right. Correct?
So
And we
here,
can actually, yeah.
no, sorry to interrupt. Sorry, please go ahead. Sorry.
So this one doesn't require a secondary proof or somebody's certification that is my approach correct. Okay, the approach is correct because it was able to solve the problem. Okay, in a reasonable time. All right.
So here with multiple weights, again, we will use the eta function, that eta thing, like what
Yeah.
we are going to do that, right?
Yeah.
So for every weight, then we will say
Yeah,
that,
just
okay,
like
how much the
yesterday we
jump
did.
weight.
Yeah, just like yesterday we did. Yesterday we tweaked only two variables. We'll try to tweak two variables and then we'll try to tweak all the variables. Okay?
Yeah.
All right, perfect. So what we have,
this learning rate scheduling, right? You said these their strategies. So are we going to discuss them later?
Yeah, in the class it's going to be there. They're going to be differences between various approaches and so on. Okay?
Sandeep, so that dimensional reduction you were telling about, that includes reduction of both rows and features?
No, features.
Okay, so like, do we also benefit from reducing the rows or just?
No. If you see here, when we say epoch equals to 1,000, it's like replicating number of rows 1,000 times. We are running the loss over and over 1,000 times. Correct?
Yeah.
So that's the thing. Okay. For every time we are tweaking these values and then we are again picking the same row. So basically, more the experience, better it is for us. Okay. The reason that ChatGPT is so efficient and good is because it has gone through so many rows of data. Okay. The prompt size, okay, the way you should think about it, the prompt size is equivalent of features, number of features. Okay. And it's equal to number of features. Okay. And the experience of the right, the data crawled from internet is roughly analogous to your number of rows. Okay. So the data that you have, number of rows you have in the experience, is only needed at the runtime, at the training time. Correct? We crawl the data, we trained our model. Now, once the model is ready, we have weights. Now we can run it and we don't have to worry about how much data it was trained on. So more the number of rows, better would be your model. More the number of columns, difficult it is going to be to train it. Okay.
So Sandeep, how do we decide to control the cost of the training? If let's say we have got a lot of data, but we want to train the model with, let's say, some number of rows, but we don't want to kind of train the model with all the rows. Or maybe can we reduce the test data?
Yeah.
But then if you're saying more rows, we have to train more, then the cost of training will keep on increasing.
Right. The only case where we want to reduce the number of rows is the only clever strategy that people come up with is basically this way. What you do is you, number one, okay, if you have like too many rows is a good problem to have. Okay, too many rows is a nice problem to have. Okay. It's like saying that what if I get too much money? How will I store it? It's like that. Okay. So too many rows is a nice problem to have, right? Meaning we have more data points, our model will be more accurate, right? So if you have too many rows, then what you do is you don't train on the model that have to load everything into the memory. Okay. So avoid the models that need the whole data in memory, whole rows, all rows in the memory. Okay. You avoid things like example is SVM decision trees. Okay. There are quite a few algorithms other than the gradient descent. Okay. So you avoid SVM, decision tree, and so on. Okay. If you have too many rows. Okay. Right. You do the batch wise training. Okay. Meaning you will load, let's say, how many data can you do it in the memory? You will load that much data, find the error, and optimize MNC, your weights, and then load another file. Then again, using that file, you'll compute the loss, and then you have to tweak the weights. Then you load another batch. You keep on loading batch wise. Okay. If you have just too many rows, okay. These are rich man's problem, by the way. Okay. If you have too many rows, this is how you're going to solve. You do the batch wise. You load one batch, tweak the weights, then again load another batch, tweak the weights, then load another batch and tweak the weights. Okay. And still, if you are really don't want to do this, what you do is you do the sampling. Okay. Sample the data. Okay. That's another strategy. Other strategy is deduplicate the data. Okay. What you do is you sort the data and remove the data which has too much similar with each other, and then you come up with those strategies to deduplicate and just keep only the unique, very unique values to each other. Okay. So those are the few strategies, but the strategy that is there in the market is this. Okay. The reason why gradient descent became the algorithm of choice is because of this, because you can do batch wise. Right now, this problem that we are having here, right, we were running epoch. We could also do here that we basically for each batch, right, here you could say load, right, for each batch or for file in files. Okay, you have like 100 files. You load the data from 100 files in X and Y. Okay, right? X equal to open the file. Okay, open and read file. Y is also okay. So you kind of define this function, and you'll basically for each of this, for each file, you will start finding doing this operation, and then load another file, and that's how you'll do. Okay. And then once you're done with all the file, then you again start from the first file onwards. Okay. So the beauty about the gradient descent is that it can handle the data in batch wise. All other algorithms need the data to be in the memory. They need all of the data together. Here, what we are saying is we just have to compute the loss. We can just do it batch wise. Okay. Very, very good questions. I hope we are on the same page. Did I answer your question?
Yes, certainly. So do we have other algorithms like gradient descent which also do not require data to be loaded in memory?
There are some, but not that great. One of them is XGBoost. Okay. And there are those kind of ones. Okay.
But Sandeep, like if we have to deduplicate the data, we anyway probably have to load everything in the memory, right?
Yeah. That's why you will have to go for, let's say, distributed computing or a strategy where you can, do the disk sorting in the disk, as I said earlier, that in part divide the data in parts, sort it, and then merge it and do all of that. Okay. So
And
deduplication is,
before doing all this, we will have to means we would probably run the this dimensionality algorithm to reduce the
yeah.
dimension for the features.
Yeah, if your features are too many, then that's another issue. Okay, here we are talking about if there are too many rows. Okay, so you'll have to think about columns in the different way. Okay, yeah.
Okay. And
So you'll have to, in that case, you'll have to apply both the things. All right, all right. So this is the reason why, I mean, learning other models may not be that helpful. Okay, just that there are few companies or few organizations who don't like neural network. Like for example, let's say a bank would not like to go for a neural network. Okay, in that case, what they do is they'll go with, say, decision tree. Okay, a simpler algorithms, simpler models. Okay, which are more interpretable, which are more easier to understand than neural network. And what they do is they use the neural network, like the complex systems, to just establish a benchmark. Okay, so that they can tell the data scientists that, hey, using neural network, we were able to achieve this much performance. Can you match that performance? Okay, if their data scientists are coming back and saying, this is the best we can do, you can tell them that, hey, neural network is able to achieve that much. Can you achieve that much? Okay, so yeah, so that becomes like a kind of for benchmark. Okay, so
So
coming
why
back
don't they use neural networks? Is it because of too much data?
no, neural networks are, after a while, they become, you just like when you look at the human mind and you say that it's difficult to understand the human mind, right? Similar to that, neural networks become impossible to interpret, right? ChatGPT is giving a result, but nobody can tell how exactly it's thinking about it. Okay, and therefore neural networks are avoided in some organizations, some traditional organizations where interpretation is more important. Okay, and interpretability of a model is inversely proportional to its quality, right? If somebody is so easier to interpret, right, and that person would be having a smaller mind. Okay, like for example, if, let's say, we know very clearly that pigeons are attracted to the food grains, so we can throw the food grains and they come, and then we can catch them by throwing a net, right, by putting a net there. So if, like, pigeons have a smaller brain than human, because human is able to interpret the pigeon's mind and then utilize it, right? So intelligence is inversely proportional to interpretability. Okay, so the neural networks are much more intelligent, much more complex, and therefore are very less interpretable. And therefore, what people do is they avoid neural networks only in those situations where there is a need of interpretability. Okay.
So isn't there some research going to make neural networks more interpretable?
There's
Or it's not
going to
possible?
be, but my hypothesis is this, that research is not going to be very useful, because
Okay.
intelligence is inversely proportional to interpretability. The more, it's as simple as that.
And the decision trees can give an actual explanation of why did it arrive at a result.
Uh, I think um, it's not going to be. Okay. It's not going to be. And yeah, I think I think it's very clear. It's very clear that interpretability is inversely proportional to complexity.
Now, my question was models like decision trees, right? Are they able to explain why did it arrive at some result?
Yeah. Because you are able to print the if-else conditions, right? If this is this, then do this, then. So people are able to look at that. Okay.
Oh, thank you.
Sandeep, in case of dimensionality reduction that you what is the topic? What if columns are very less but rows are very high? In that case,
That's what we are talking about right now. Yeah. So if you have too many rows and too few columns, it's a good news. It's a good news. Okay. There are some strategies where we convert the few rows into multiple rows. We'll talk about that. The example is, right, converting few columns into multiple columns. Okay. It's called factorization method. Okay. The Netflix challenge solution is one such example. Okay. In Netflix challenge, if you know that there was this Netflix challenge. Okay. Okay. This one. Okay. So what was given is that you were given 1 million ratings of movies. Okay. It had 3 columns. Okay. It had right. It had user ID, movie ID, and date. Okay. And based on these 3 columns, like the user ID, movie ID, and the date, we had to predict what was the rating that the user has given. Okay. Here, there were only 3 columns and 1 million ratings data. Okay. So what they did was they did opposite of what we do in dimensionality reduction. They converted one column into multiple. Okay. So take a look at this one as a good read. Okay. This is the starting point of what you see as okay, what you see as of today when you look at Kaggle. Kaggle was started after this Netflix competition. It was a $1 million competition, and it's a landmark thing that happened in 2011 or 10. Okay. All right. I hope this is clear. If too many rows, it's a good news usually. In some cases, one of the cases where you convert the few columns into more columns, utilizing too many rows. And basically, you do the batch-wise training. This is the most important part. And this is the technique that we'll learn as we go ahead, that how do we train batch-wise, or how do we do it in a more, more efficient manner. Okay. Everybody.
Is it okay to conclude that large models like ChatGPT, they will be using some variation of gradient descent?
Yeah, they are, of course. Entire thing is on, there is no other better algorithm. They are using gradient descent, there's no doubt. No doubt. And they are using batch-wise training, otherwise they won't be able to train on internet's data. Okay. Of course. Absolutely. All the papers that you see, they are just using some variants of gradient descent. There are some variants of gradient descent which are distributed in nature. We'll talk about that. Okay. All right. So what we have here is that we defined our loss function, which takes an array of weights. Okay. Array of weights. These weights will be one more than the number of columns in this data set. This X has got rows and columns. Columns represent features, rows represent experience. And we're going to go over all the rows and compute the error in each row, and then compute the square of that one and sum it up. and that'll be our overall error. Okay. Perfect. Everybody good with this? I'm going to leave this one, and there we go.
Just one more question. Is it possible to predict the cost of training a model so that we can decide how many dimensions we can afford to drop or afford to train on?
Is it what?
Possible to predict the cost of training the model?
Okay.
So that we can decide that we can't go with, let's say, 10 dimensions, we can only go with 6 dimensions. Is there a mechanism or structured way of doing that?
So yeah, usually you will see very often that I mean, as I explained to you, right, the lower limit, okay, the number of rows should be one more than the number of features, minimum. Okay. And further, my suggestion will be that at least it should be double, at least double. Okay. So in the cases when you have like both to be equal, and like let's say you have 500 columns and you have 1,000 rows. Okay, you should apply dimensionality reduction to bring it down to say 10 columns and then get it. This is going to be a better model. Okay. Again, do all of these strategies, okay? All of these strategies in order to optimize your error. So what you usually do is take your total data, okay? X and Y, break it into two parts. We call that training data and test data. And what you do is you keep on training and keep on applying all your strategy on this data. And once you're done with it, then you evaluate which of the strategy is performing great on the test data. Okay. Most important part to keep in mind is that there is no right or wrong as long as you are getting the results. Okay. All those hypotheses, all of these gyan I'm giving is only valid if that gyan is helping you getting better results on test. Okay. Otherwise, your model, your strategy is not, all of that knowledge, all of that gyan is useless. Okay. So whether you are dropping the dimensions, okay, or you are coming up with better dimensions, you are coming up with better model, or doing whatever you want, you should always evaluate against X test. You don't need to come back to me asking, Sandeep, do you think it's a good strategy? My answer will be that go and test it on test data. Okay? Whatever works, works. As simple as that. And I can tell you this, that even the Nobel laureate, the guys who got the Turing Awards for the model they built, right? Their next paper got rejected because it was not performing great on the unseen data. It was performing great on the seen data, but not on unseen data. Okay? So no matter who builds the model, doesn't matter. What matters is it doing good on actual data? As simple as that.
Don't try to do too much of sampling or deduplication on test data. Is it correct?
Yeah. Don't just keep it away. Otherwise, your brain is very, very, very smart creature, right? It just will basically figure out what works best for that test data. You'll kind of, it's like seeing the exam paper and only preparing for that. Okay. So don't look at your test data. Just you're given the data, split it, keep a part aside. Don't look at it. Don't let your models look at it. Once you're done with all the fiddling, then you go back and compare your results on the test data. Okay. All right. Okay, so I hope everybody is good so far. So we defined a loss function. Let's just see the loss function. Is it working? Okay. So we are passing it X and Y. Okay, we are saying, okay, how many columns do we have? 1, 2, 3. Okay, so we'll have one more weight than the columns. So we have 2 columns in X and Y. If you see, X0 has how many values? X0 has 2 values, and therefore weights will be 3. Okay, and we are passing X and Y. Okay, the error is this much. We say, okay, we increase the X little bit. Okay, the error has, okay, the error has decreased. Okay, error has decreased, so we can increase error X to 10. Okay, all right, something like this. And this is what we are going to do strategically. Now, this time we are increasing, okay, we are just keeping this value same, okay? We are increasing 2 a little bit. When we increase 2 a little bit, the error is reducing, correct? Therefore, and similarly, if we increase y a little bit, this third variable a little bit, the error is in reducing. What happened to the error? What happened to error? Yeah, reduced. So all of them need to be increased. As per this, all of the values need to be increased. Let me just increase all of these values. Okay. So now my error is this much. Okay. Now I'll start from here. We'll try the same strategy. Okay. Increase X a little bit. Did it drop or did it? Yes, the error is reducing. Okay. Now, okay. Did the error as compared to this one reduce? Now, this is painful to do it manually, so we will do our gradient descent. So for each of the variables in the weight, we'll try increasing one of the values, observe whether it increased or decreased, and that's it. Okay. So let's compute the, okay, we will call it diff p. Okay, we'll compute the difference, and we'll increase one of the value by delta, and then we will try to see whether the error is reducing or increasing. So we are giving the function because we want, rather than we calling this function again and again and trying to check it, we want this function to do it automatically for us. So we are passing the loss function, okay, this function in the argument, okay, and then we are having certain weights, okay, the arguments weights, and then we are basically having X and Y given to us. Okay, so what we are going to do is we're going to take we're basically going to just do the way we increase one value at a time, the way we increased one value at a time and observed. Similarly, we are going to basically take this index and observe. Okay, so previous loss, okay, previous loss before increasing the weight is SQ loss, okay, on these weights. All right, and again, I'm going to make a copy of it so that I don't end up overwriting it. Okay, so I computed the previous loss on this X and Y. Okay, now I increased one of the value with delta. Let's say the delta is very small number, and I'm calling it 0.0000001. Okay, and then I'm computing the difference. Okay, difference equals to difference in error. Okay, difference in error is equal to how much? Or let's say loss. Let's just keep loss. So new loss is how much? New loss is, okay, new loss is this much, right? We increased one of the values and then we say new loss minus previous loss, okay? And we return the rate of change of loss, difference of loss divided by delta, right? Because of changing that particular variable by delta, we occurred this much loss, okay? So let's just see. Okay, so in case of, let's say, SQ loss, and our weights are 1, 2, 3, and our X and Y, and we are saying, okay, tweak it with respect to 0. So you can see, because of increasing first value, the loss is negative, which means that loss is dropping because of increasing first variable. Okay, similarly, let's check with respect to the first variable. When you increase 2, what's going to happen? It says that it's still, right? You need to increase 2 in order to drop the loss, right? Everybody okay so far? Okay, so we defined this function which can compute the rate of change of loss with respect to each of the weights. Okay. Now, what we are going to do is we're going to say for epoch in range, let's say 100, okay? And we're going to make a guess, okay? We're going to make a guess how much, right? So we're going to say for I in range. So how many weights should we create? Okay, our weight should be one more than the total number of features, correct? And that's why we are just saying random.random. Okay, so we are initializing weights to be random. Okay, and here what we're doing is we are essentially this is how we are initially essentially randomly generating all the weights. And then, like the way here our randomly chosen weights were 1, 2, 3. Okay, the total number of columns in X is 2, so this length is 3. Okay, W0 is extra. And now what we're doing is on every epoch, we are going to do the same thing. Remember this thing? Okay, this part. Okay, let's take a look. Okay, let's take a look. So what we're going to do is we have these weights. Okay, then what we are going to do is rather than calling it manually, we are going to say for, right? For I in enumerate weights. Okay, for each of the weights, we are going to compute the rate of change. Okay, we are going to say DE as an array. Okay, we are going to put the loss that we calculate for each of these variables. Okay, this is how we calculated the loss for each of the variables. Okay, all right, so we went over. Basically here we were doing it manually 0, 1, 2. Here, instead of that, we put it in a loop. Okay, and whatever is the result, we are essentially just appending to this. Okay, we're appending to that array. So this array contains all the weights. Okay, now all we're going to do is once we have calculated all the gradients, now the way we applied here, okay, So this part has been replaced by this logic, correct? This part has been replaced with this logic. This part, okay, this part has been replaced with this logic, okay? This is initialization, okay? We replace, instead of doing it manually, we basically just used a loop, okay? So that we can generalize it for any number of columns. Yesterday, there was only one column. Today, we are trying to do is for any number of columns, okay? So this is our initialization logic, okay? And, okay, we can also define them like a function and then use them. Now, here is, we're going to give it a try, and we'll keep on printing the current loss, okay? And current loss, and we are just passing X and Y, okay? That's about it. And then what you're doing is here, first we compute the gradients for each of the loss for each of them, and then gradient here using the diff, what was the algorithm? Yeah, diff p, we computed the gradient, the rate of change of the error, okay? And then we're going to do this tweaking of the weights, okay? So we're going to say for I in range, what is the length of this DE? Okay. We are going to say weights minus equal to eta times DEI. Okay. That's about it. That's it. Cool. All right. Are you happy with this?
So Sandeep, the one which we did earlier, the last week classes, which we did on Excel one, so that we tried to replicate to.
Yes, 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 yes. That's what we are coding it here.
Nice.
Okay. All right. Perfect. Let's see. It says syntax error. Somebody help me fix it. Okay.
Oh.
Okay. All right. Why is this? Oh, is this too many variables? Oh, okay. No. This has to be x0. Shouldn't it be like this? What is this delta? Who can help me fix it? So first error I spotted was that here I basically found, instead of counting the features, I ended up doing it for the rows. That was wrong. And then, okay, so let's just separate each part of the logic and do it independently, okay? So there we go. All right. So let's see, did I do it right? Okay. So you can see there are 3 weights that it has come up with. That's correct, because there are 2 columns, 2 features, x1, x2. So W0 plus x1, W0, W1, and W2, 3 variables. Okay. Now we are saying compute the loss. Okay. So loss was correctly computed, right? So what does the loss function take? It takes weight and it takes x and y. We are not touching x and y, right? Let's just see. X, how much is the length of x and length of y? Okay, both are 99 each. Okay, now we are having this and this, and we are trying to print loss and weights. Okay, fine. Then we are saying enumerate over all the weights Okay, here. Okay, or let's just say for range, and we'll just say length of. Okay, so we are saying compute the diffp of this weights, and then for each of the weights, we are essentially computing the rate of change. This is perfect. So this should be okay. And then we are applying the ith weight on each of them. Okay. Now where we have to say weight of I. Okay. Weight of I. Okay. Now we are at a good position. We'll say eta equals 0.001. Now we are talking. Okay. So earlier the error was this much, then error became this much, then error became this much, the error became this much, and then error is this much. So error is definitely dropping. You can see error is definitely dropping. Okay. Okay, error is dropping. Yes. Okay. All we need to do is do it for more epochs. Okay. Error is dropping, you can see. Okay. All right. Perfect. So here you can see we kind of have saturated the error. Okay. So as per this logic, the equation that turns out to be W0 is 66, W1 is 100, and W2 is 300. So our Y is equal to, you can say 66 plus W1, 100 x1 plus 300 x2. Okay, this is the equation our model has figured out. Let's see how close is this. 100. Okay, the actual one was this. Okay, so it has figured out those variables very cleverly. Okay, removing the noise from the data. You can see it basically figured out that this is a random noise, and it figured out that this is almost 100, 100.6, 100.6. Okay, 100.6, and here this is 66.3. Okay, so actual was 67, and this is 66.3. Actual was 300, ours is 300.1. You see that? And that is because of this random data. Are you guys happy with this? No? Yes?
Yes, yes.
All right.
I need to check the program that you wrote one more time, please.
Yes. You guys should take a look at it, right? This is the key part of the TensorFlow. The other things that we want to discuss further is this, right? You can see here, okay, it's just too much painful. If you see this much, this is too much painful. There's an array of numbers and we have to subtract all of them with these values. So we have to keep writing the loop. What if we could just subtract two arrays from one from another, right? That could be just good enough. Or we could just multiply one array with another array, and that will solve our problem. Okay, so to reduce all of these for loops, people devised something like NumPy. Okay, NumPy basically let you subtract one array from another array, take one array, multiply with another, and all of that for loop is not required. This code can be simplified to couple of lines, not couple of lines, couple of paragraphs, by using the NumPy way of multiplying things. Okay, so I hope this is good and clear to all. Okay. All right.
Sandeep,
Just for the
just
record,
one
yeah.
thing. So this is like all problems you are solving now. So this looks like very generic. It looks like for all the prediction problems. So some generic problem, if solution is there,
Yeah.
so it can solve all the problems. I want
Yes.
to, right?
Yes.
So
Linear problems it can solve, and you can also create your own loss functions and own kind of models, and then it can come up with those values.
okay.
Okay.
Means I want to say like normal algorithms. Therefore, all problems we write different code, right? For here,
Yeah.
So there is no like it looks like if one time I have done something, almost it is done, right?
Yeah. Yeah. So all of this is part of model.fit. You'll get a model.fit. Okay.
Yes.
And right, people wrote all of this as part of TensorFlow and scikit-learn. So all of these algorithms are available in TensorFlow. Okay.
Okay.
TensorFlow and scikit-learn. You don't even have to write any of this. Okay. And right, and basically you can utilize this these things by just from TensorFlow and scikit-learn. Okay. I hope this was useful, everyone.
Yes.
We took yesterday's one and generalize it for any data set, any number of columns. Okay.
Is this algorithm used mainly for linear regression only or for polynomial also?
So what do you do in case of polynomial? That's a good question. Okay. Can I use this? Can I use this for polynomial? Okay. Polynomial, right? That is the question. Okay. Now let's take a look, right? Say for example, our data set was like that. Okay. Yeah. Here I'll have to just what all do I have to change? Nothing, right? I don't have to change anything. Good. Okay. Imagine that we have this data set which is generated from, there is a secret equation, let's say here. Okay. You can actually just do this. Okay. Let's see. Okay. Internally, let's say it is this. Okay. X square. Okay. And we don't know whether there is x square or not. Okay. This is the equation internally. Okay. Now we generated the data. Cool. So we have two variables, x1 and x2, and we have y. The number of columns are same. So we have x1, x2, and we have y. Okay. Now we realize that this data set, this one, okay, this data set basically may have non-linear relationship with input and output. Somebody told us that there's a non-linear relationship, so be aware. Okay, so we started, what we did was we took this data x, right? Okay, and we went through each of the columns. Okay, so we said, okay, this is x1, this is x2. Okay, we will add one more column to it. Okay, with value x1 square and x2 square. Okay, we added these two columns, and we also added x1 into x2 as part of this. Okay, so now we have 1, 2, 3, 4, 5 columns. Okay, so let's just generate that. Okay, so we said, okay, our data might have the correlation like this. So what we did was for row in x. Okay, and this is my new x. Okay, so what we did was we said new x dot append. Okay, and let's call it, let's say x1 comma x2 equals row. Okay, and we are saying let's keep x1 x2, and maybe there is x1 square and there is x2 square, and then there is x1 into x2. Okay, so we basically have put this in here. Okay, so my new x looks like this. Okay, each of the variable column, each of the row has how many values? 5 values. Okay, now we go back here. We go back here. All right. Okay, now we are saying eta is this, epoch is this. Now we are initializing number of weights. First, we have to initialize number of weights. Okay, where is that logic? This one, right? Number of weights. Okay, we have to initialize, right? Number of weights. Good, we initialize the number of weights, and I mean the initial value of weights, and then we started just using, okay, y is there, new x, y, and is that it? Yes. Okay, so you can see it's reducing the weights, right? Yes, it is reducing the weights. It's reducing the loss, you can see. But it's reducing super slow. Okay, we have reached here. Okay, and I hope we are doing right. Ah, here, this is where we made mistake. Okay. All right. Okay, so let me see. Looks like okay to me. Let me just run it like some more times. Okay. Loss has gone down. I'm happy about it. Okay. Loss has gone down. Yes, it's still going down. So I'm going to run it 1,000 more times. Loss is still going down. Okay. It's still going down. So I'll just run it 1,000 more times. Okay. All right. Let's see. Okay. So here, this is my model that came out. Okay. Okay. This is the model that has come out so far. Okay. Do you want to run it more? Let me just run it more. Let me just run it a couple of more times and so on. Okay. Let's see. Was it able to guess our actual value? Yes or no? And then, okay. All right. Let's see. Okay. So let's say this is our final model. Okay. This is the final model that came out. Okay. So we are saying our y is equal to, this is our W0 minus 8 times of x1 plus this much time of x2. And this one is x1 square, isn't it? Okay. And this one is how, what? x2 square. And this one is times x1, x2. Okay. So you can see that here, these values are very tiny. You can see minus 8x, right? And here, these values are also very tiny. x2 squares coefficient and x1, x2's coefficient is also tiny, correct? So what we can do is we can ignore them. We can ignore these coefficients, okay? we can say, oh, let's just, and okay, let me put it this way, that this is our model that has been figured out by this guy. Okay, this is the model that has been figured out by this. Are you with me, everyone? Okay, this is the equation that has been figured out by our gradient descent. Okay. Yes. Okay. What was the original? Original was, where was the original? Original was this. Okay. So original equation was this. Okay. Where this was 67 was a beginning and 0 times x1. Okay. You can just match column by column and okay, you can see that. And yes, not bad after all. Okay, and then 0 times x1 square and 0 times, sorry, x3 square and 0 times x1 into x2. Okay, so you can see that instead of 0, our model guessed it to be close to 2. Instead of 0, our model guessed it to be 2 across close to 2. And instead of 100, we guessed it 100, not 6. Instead of 300, it guessed it to 296. And instead of 0, it guessed it -8. And instead of 67, it guessed it 69. You see that? All we did was we added the columns corresponding to that. That's all.
It's pretty close.
Pretty close? Yes. So we have created a machine that can solve most of these problems. See that? We did not have to change anything at all. Okay. We only had to add columns and that's it. So polynomial regression, you can just do it this way.
So to
Right?
make it more closer, do we need to run it more times? Do we need to play around with delta and
Which one?
for making this polynomial one more closer to the actual equation?
No, this is good. This is good. This is how you would do it. Okay. Yeah. At the end of the day, you basically have to keep minimizing the loss. Maybe you can just run it a little bit more, probably a little bit more. Okay. So I have just ran it a little bit more. You can see it's going down. Okay. You can just keep on beating it until it goes to that. So you can see this one has already gone to 0. This one is also going to 0. You can just keep on forcing it to go through the data multiple times and that's it. Okay. So it's kind of, yeah, I think this is okay. We can forgive this here. Okay. You can see this one has already gone to 0.08. Okay. So, and the loss is not going down much. It's just going down slowly. And okay. So the thumb rule is that as long as the loss is going down, keep going down, keep running it again and again. Okay. What happened here? Suddenly, why did it start increasing? What happened here? Did you make a mistake somewhere? Oh, something went wrong in the midway. Okay, never mind. Okay, never mind. All right. Okay, so usually you will keep on observing your loss, and you will observe the loss on test data also. We have not talked about it, and we basically have focused more on building this. Now, right? So yes, I think whatever we have done so far, I would want everybody to just code your own gradient descent. Okay, and we will talk about the normal equation next week, and we'll also talk about NumPy pandas, and then we will start with end-to-end project, and then with machine learning. Okay. All right. Though these previous couple of sessions and this one, I would want everybody to just be very comfortable with the gradient descent. Okay, and it's possible to code it, right? Probably you guys can just code it in an interview of 10 minutes, not 10 minutes, maybe 20 minutes. Okay. So you should be comfortable with it. Okay, you should be able to, you don't have to memorize it. You should just know that what to do in what scenario. The situation would be that if I do this, if I increase number of iterations, what's going to happen? If I do this, what's going to happen? And you'll be able to answer those questions only if you basically only if you basically have experimented a lot, right? Right. A simple thing would be, what would happen if there is no W0, right? Why do we need a bias? We call it bias, by the way, a W0. Why we had that discussion. So all of these things, the way usually I ask, or anybody for that matter would ask, the question around gradient descent would be, where would it not work? Why would it not work? Okay, we'll talk about a lot more scenarios. Okay, and I think that's pretty much. So good. We were able to create the entire algorithm during the session. I hope this would. I hope that all of you are super clear about that this can be done. Okay. One thing I hated about the books, I remember there was one book in which one small problem was in 20 pages, making me believe that creating a algorithm is so complex that I have to go through all of that. And then I looked at Kernighan and Ritchie, KNR, by those guys who have created C. They had written most complex code in 10 lines, 20 lines. That gave me a lot more courage that, okay, this seems easier and more straightforward than what I have read elsewhere. Okay, so with that, the agenda, why I did the coding, I could have just told you to go through some other notebook and something, just to make sure that we get this courage to just code it up. Okay, I would want everybody in the class to finish writing their own version of gradient descent by next week. Okay, test it on all kinds of data. The way we tested on square, cube, and so on, you test on others also. All right, so have a good day. Bye-bye.
Thanks, Sandeep.